Very good afternoon, everyone. Today again, I think only one or two participants are here, Gagan and Siva sir. Although I requested all that please join today's class, it's important. Today I'm going to discuss multiple regression because now with most of the derivations we have done, so it's now the time to apply all those derivations and try to understand how we get results in regression. So before starting, let me, as I told you that in part 3, our focus is on cross-sectional data and quantitative dependent variables. Means I told you there are many combinations of variables and types of data in the regression models. So this particular series is about this particular combination, cross-sectional data and quantitative dependent variable. No restriction on the independent variable. It might be dependent or independent. I hope now I'm audible, Siva sir. It might be earlier my actually this mic was switch off. I hope now I am audible. Okay. Okay. Thank you, sir. I shared 2 or 3 data sets today. These data sets are from the Woolridge that I told you that I'm arranging those data sets from the help from few students. So first start with this multiple regression. That what is multiple regression analysis? Generally, when we have more than one independent variable, that we say as a multiple regression. Earlier in the bivariate, we did these examples, the impact of education on the wages. Let's suppose now I have added one more variable, experience. Now, if we have more than one independent variable, then we say it's a multiple regression analysis. Now, here the interpretation and derivation, everything will change. Although I did with all of you this matrix form, that derivation is for the multiple regression. Might be you have a 3 independent variable for up to a k independent variables. With matrix method, you can derive the estimates. Sorry. So here, let's suppose we want to, we are interested to find the impact of education on the wages and experience on the wages. So these estimates like this beta 1 and beta 2, these are partial slope coefficients. That when we estimate this beta 1, that will tell us that with the change in education, how much is the change in the wages, keeping all other variables constant. So these are the partial slope coefficients. So today first I'm going to take this example. This example I have taken from the wages data file, wage1 data file that I have shared with you. This particular file where you have a variables, this wage, education, experience, tenure and all. So if you regress, means first dependent variable, then your independent variables, you will get these results. So as I told you yesterday, so far we have done till this all these calculations and R square. We are only left with this particular table, this ANOVA table, and this F ratio. That how these values are derived. So today I'm also going to come to this point, this particular table. This is regarding this F ratio, overall significance of the model, and all these values. So now we have more than one independent variable. So it's a case of multiple regression. These are the coefficients. Now Stata is providing these partial slope coefficients. What it means is that first you have to look upon the data that how this data is look like, means this particular data set. Let me just open the data editor window. We have a wages here. It might be in dollars. Maybe this data set is from USA. And these might be per hour or per day. That actually I don't know, but let's suppose these are per hour, just hypothetically. Then experience you have, let's suppose this is in years, and education in number of years. Okay. And you have this theory, means behind the model, means first that steps will remain same. First it needs to be some theoretical framework, and then from theoretical framework we'll find independent dependent variable, then mathematical model. It might be x square, x2 square, x1, that depends upon the relation and your understanding of the mathematical relations and functions among the variables. Then by adding this residual term, we convert into a econometric model. And after econometric model, the first task is to estimate these, to derive these estimates, partial slope coefficients and intercept term, to get this impact of education on the wages and impact of experience on the wages. So for that, we need some regression analysis. And here we are doing this OLS method to estimate these. Again, I'll come later on to the degree of freedom. So far, just focus on these estimates and ask, I'll come to a degree of freedom when it will come to a F ratio. So here, first, you have to estimate this with the OLS method. So far, we have done this OLS method. And I told you there are assumptions with the OLS method. And if those assumptions will fulfill, then only these blue properties will be proved. That is linearity, unbiased, and minimum variance, efficient estimators. So let's suppose you have this model and you have this data set. Now today, this exercise for you is the manual process. You have data for y, for x1 and x2. With this, now you have to estimate these coefficients manually because I have already given you all the formulas. Today again, just to remind you back, I'm going to give you all the derivation of these formulas for these coefficients, R square, F ratio, and all these values. And that you have to calculate with the manual process. You have a data of y, this dependent variable, x1 and x2. So using this, you have to calculate these manually. You have the data sets. I already shared the file. And these calculations you have to share this Skype format. Means I have to see whether you are doing it or not. Because from last 3 or 4 days, maximum of you are not attending the classes. So there is no purpose to discuss these things in detail if you are not interested. And continuous absent is indicating that maximum of you are not interested in this part. That's something which is not appropriate at this time. Is we are putting so much effort on this that all the derivations from different books. I'm trying to give you maximum explanation for all these concepts in detail. Hardly you are going to find these all the concept in so much details when we teach in the classrooms in the semester system. The actual problem with the econometric course is that we only have a 50 and 55 hours in a one semester to teach this whole course. So there is a limitation to teach everything in a detail. So here we don't have that limitation, although I also have a limitation of the time, but I am trying to give you as maximum derivations as possible so that you can have this confidence that how these values are calculated. So the only difference after this course among you and the others who are doing is that at least all of you know that how these values are calculated. Means that's the difference. Otherwise, anyone can from the command stage I can just type the command in this data and get these results. But to interpret it accurately and to find the problems in the model and how these values are derived, that now you can understand because you are doing it in a detail. So that's very important. Today I'm going to give you this exercise data file. I already shared this wage1 file. From that file, you have a y model, that is y variable, that is wage, education, that is x1, experience, that is x2. Now I'm going to share all the formula again for these coefficients, standard errors, t, r square, f ratio, and all these values. All these values. These are the actually explained sum of square, then residual sum of square divided by degree of freedom, then it is a mean sum of square for explained part and for the residual part. I'm going to share these formulas as well today. and then you have to put these formulas, your data that you have to do all the calculations, and you have using these formulas manually. You have to calculate these values, and you have to cross verify the Stata results which is giving is equivalent to your results or not. Might be we did some mistake in, let's suppose, in any derivation or writing any formula. There you will get different results from these Stata results. So that's also important. And for the practice purpose, that's also important that you do this manually. So this exercise is now a homework for you that you can do on Saturday. I think Saturday is Diwali, so I am not going to take any class on Diwali. I know you all are going to engage in your with your family and friends. So on Saturday there is no class. So maybe Saturday you can do this exercise, or tomorrow or today. Choice is yours. But at least till Sunday I have to see this in the Skype, this exercise by all of you. Otherwise, I'm not going to share all other details like I'm sharing through the YouTube if you are not doing this exercise. So now one by one, and this is the basic, actually basic most important part of econometrics, and later on we are going to deal with the problems with the assumptions from the next classes onward. So today, now again, just understand all these values in detail. First, I'm going to share this coefficient, how you have to derive these coefficients. Either you can use matrix method. I already shared with you matrix method formula for these estimates, beta matrix, and for the variance as well. Either another simultaneous equation method today I'm going to share with you again. You can use any method, you will get same results. So this is very important to understand these values. Then only you can understand these problems: multicollinearity, hetero, auto, model specification test. There's all those other problems which we study in econometrics that you only understand if you have a understanding for all these values in detail, and you know how these values are going to change and which thing going to impact these values. Then only you will understand all the remaining part of the econometrics. And if you don't have understanding about these values, then there is no other way one can teach you the econometric things. So let's start. Initially, we have a bivariate model where we have a independent one independent variable. In that case, your normal equations, which we get these normal equations after differentiating which equation? We differentiated a equation that is summation u hat residual square, right? Ui square. And that equation we are trying to minimize. So we minimize that particular equation. Let me, if I'll go back, that how you got these two equations in the two normal equations in bivariate analysis. Let me just get back so that you can understand once again this process. Yeah. You minimize this particular equation, right? This residual actual value minus this estimated part. We differentiated it with respect to beta 1 and beta 2, and we got these two normal equations. With these two normal equations, we derived value for beta 1 and beta 2, right? This is slope coefficient and the intercept coefficient. This is we did for the simple OLS method in case of bivariate. So now if we have a more than one variable, again the process is going to be remain same. Again you are going to first summation u hat square, and that you are going to minimize. So the change is that now in place of one independent variable, we have a two independent variables. So now you will get these three normal equations because you have to estimate three estimates. So you will get three normal equations, and these equations will come if you differentiate this summation u hat square with respect to beta 1, beta 2, and beta 0, your intercept coefficient, then you will get these normal equations. If you want, I can just give you this example in a brief that you can understand this process once again. Let me solve it again for you so that you can understand these equations. And if you solve these equations, then you will get these estimates. Intercept coefficient, beta 1 hat and beta 2 hat. Let's suppose this is a coefficient for your model for education, and beta 2 is for experience. This is the formula, means if you can put these values here, all these values from the actual data, you will get these three values, education coefficient, experience coefficient, and constant intercept part. So these three values are from these three formulas. How we get these three formulas? Just in brief, I'm going to explain you once again, although we already did this with the bivariate method and the matrix method, but just in brief, let me give you this example once again. Let me see if I have a space here. Okay, let me do it in a side. Let's suppose our model is y1 equal to beta 0 hat plus beta 1 x1 plus beta 2 x2 plus our residual term. If you are doing from Kotsianis, they write this residual term for the sample regression function as EI. It is actually U hat or EI. This is just a change in the notation. So if you have now, which thing we have to minimize? We have to minimize this thing, okay, that you have to keep in mind. Now, this is what we are minimizing in the OLS method. So what is the value for this particular residual part? So this residual part, this EI is yi minus y hat, right? This is a y hat and this is yi. This is the residual part. So if we take it in form of deviation form, let me write it in deviation form. The y hat is the beta 0 hat plus beta 1 at x1 plus beta 2 at x2, and we know this property that regression line passes through the mean x1 mean plus beta 2 hat x2 mean. So in deviation form, like yesterday with the R, the deviation form. So in deviation form, this equation is beta 1 hat x1 plus beta 2 hat x2. This is the deviation form. If you remember yesterday part, we did it in the R scale. Let me show you that part. Here we did it right. This was the deviation form. Yesterday I explained it as this y hat, small y hat is equal to beta 1 xi. That was the deviation form that we did yesterday, this proof for the deviation form. Similarly, if we have more than one independent variable, then the deviation form is, this is the deviation form. So what is our residual term in the deviation form? Small yi minus y hat. This is the actual form and this is the deviation form. Let's suppose we are going to minimize it in a deviation form. So this is, from here we have summation ui, which we have to minimize is summation yi minus y hat. I'm giving this formula so that you can calculate this manually, all these coefficients. For that you need formula. I'm just trying to give you this explanation of that particular formula. This thing we have to minimize now, same like bivariate, now just put values here. Y minus beta 1 x1 minus beta 2 hat x2 is the deviation form of this particular y hat, and this is y minus y hat is the residual term, and this is we have to minimize. And now here to find these three normal equations, you have to differentiate it with respect to beta 1 hat, and first order minima condition, it is slope is equal to 0, and similarly summation u hat that you have to differentiate with respect to beta 2 hat equal to 0. So if you differentiate these two with respect to beta 1 and beta 2, this particular part, then you will get these two normal equations, that is 2 summation y1 minus beta 1 hat x1 minus beta 2 hat x1. If you do it for the beta 1 part, multiply by minus x1 is equal to 0. The first equation you will get, and the second equation you will get y minus beta 1 x 1 minus beta 2 hat, and it is second time you will get minus x2 equal to 0. So if you solve this equation, take divide by 2 both sides and open the summations, then you will get these two normal equations in deviation form, that is xi yi equal to beta 1 hat summation x2y square plus beta 2 hat summation x1 x2 and summation x2 y1 equal to beta 1 hat summation x1 x2 plus beta 2 hat summation x2 square. So if you solve these two equations cross multiplication method, then for beta 1 coefficient you have to ignore this part. The remaining part is your answer for the beta 1 coefficient, and that is cross multiplication, right? So beta 1 hat is equal to summation x1 y1, this first part, and cross multiply with this particular part, right? Summation x2 square minus the second cross multiplication summation x2 y1 and summation x1 x2. Denominator, this cross multiplication, this part into this particular summation x1 here summation x2 square minus summation x1 x2 whole square, because it is a 2-time multiplication. Similarly, for the beta 2 part, you have to ignore this part for this cross multiplication, that is summation x2 y1 into summation x1 square, it is 1 actually, summation x1 square, and minus again this cross multiplication, summation x1 y1 summation x2 x1 x2, and divide by now the cross multiplication of the beta 2. So that is, denominator will remain same, x1 square summation x2 square minus summation x1 x2 square. So this is in the deviation form value for beta 1 hat and beta 2 hat. So now you can cross verify here. These are the values for. Now for the third component, just from the mean equation, directly you can put these values here. This is x mean, sorry, this is x2 mean. It is not a single mean, because this regression line passed through the means. Here this property. Here just if you can put these values, beta 1 and beta 2, you will get value for the this beta 0 hat from this particular equation. So this is just beta 0 hat equal to y mean minus beta 1 hat x mean minus beta 2 hat x2 mean. So this is your third component. So you have value for these three components, means your first part is done. These coefficients, right? Now these coefficients you have to calculate manually. For starting equation, we have to start with the equation. Yes, Umya. Means regression. First, you need econometric equation. Then you can start. Means if you're doing manually. And these days, the software give you the results, but at least you have to understand the process. How these softwares are giving you these values. So this part is done. Then the next part is standard error. That will come from the variance. So in the previous part, we did a derivation for variance of beta 1 hat and variance of intercept coefficient. Now similarly, again, here we need a variance part. So variance part is, this is your variance part. If we have this single bivariate model, this derivation we did for the slope coefficient, right? Now, if you have more than one independent variable, so this is the variance values for the beta 1 hat and beta 2 hat. And this is also equivalent to sigma square summation xi square minus 1 minus r. This particular equation you have to keep in mind, because while we study multicollinearity problem, there we need these equations. So this is not, you have to ignore, but you have to keep in mind that this is also a variance for these partial slope coefficients. This is the variance of beta 1 hat, this is the variance of beta 2 hat. If we have this particular model, that is like wage, education and experience. Now what is sigma square? This derivation I already proved you that expected value of sigma hat square is equal to sigma square. That derivation proof I have given you. So here the sigma square value, here you have to put this value, that is summation u hat square by n minus 3. So means in this table, these three values, standard error, for these you have to calculate these values. These are the partial slope coefficients. Similarly, you need a variance of intercept term. So here you have to put these values. X, you have this in the deviation form. That's not a problem. these x1 x2 in the derivation form also you have this, that's not a problem, but the problem is that you need a value of sigma square. The sigma square is what? Summation u hat square by n minus 3. So it means first you have to estimate these coefficients, then you have to put these values in the regression, then you have to weight minus these values, then you will get u hat values. And if you put that u hat values, take their square, then summation and n minus 3, then you will get this sigma hat square value. And if you put this value here, then only you will get this variance. And if you take under root of these terms, then you will get this standard error. So this is a long process for me. This is manual thing you have to do. So for that, first you have to calculate the variances. For variances, you need a sigma square. Sigma square comes from summation u hat square. It means first you have to calculate u hat for all these values. If you do it in a Stata, it's quite easy. Like you have to just predict y hat first, and for u hat, it is like generate u hat. It is your actual. What is your variable here? Actual variable, dependent variable. That is wage. So wage minus y hat. Y hat is the estimated value. Is your u hat value. So now you can see in your data tables, you have this u hat value. So if you take square of all these values and then summation, and if you do in the end you divide by n minus 3, because here you have a 3 estimates, that's you lose it to 3 degree of freedom. I'll come to that point, Gagan, degree of freedom in the f ratio. Then you will get the sigma square value that you have to put here, sigma square. Then all these values you have to calculate manually, and if you put all these values, then you will get variance of beta 1 beta 2, and if you take under root of that, then you will get this standard error for beta 1 hat and beta 2 hat. Is this standard error is clear? Or you need a derivation as well for this variances part. If you need a derivation for this part, let me give you this glimpse that how these formulas are derived. These formulas for variances in multicollinearity, these formulas will be helpful. This is actually equivalent to this, means if this R12, just notations different, this is the R square formula, right? So if you can put this formula here, you will get this equivalent to this particular term. Just in place of x2 3, you have to put here x1 and x2, and if you put this value here in this particular 1 minus part, this whole value, if you solve it, you will get equivalent to this variance. So these both are equal. Derivatively, we have written it in this form because in multicollinearity problem, we need this formula in the variance inflating factor. I'll come later on, I'll discuss multicollinearity. Here we need this particular dimension. So derivatively, I am explaining here that this is equivalent to this part. So don't worry about this part. Now, if you want that how this variance is come, although for variance of beta 1 and beta 2, I already took you with two separate classes. How you have to first prove the unbiasedness. From the unbiasedness part, we took some equations to get derivation of the variance part. In matrix, it is quite easy. But individually, that's a long derivation we did for the beta 1 and the intercept part. But now here, if you again need, then let me just give you in brief detail about this variance part, that how this value is derived. Yeah, yes, yeah, one more important thing. Let's suppose if you have a more than two independent variables. So how you get normal equations? That process is very simple. Let's suppose if you have xk independent variables, so just it's a multiply with the k. Like if you have two equations here, so it is first multiply with the summation, then with the multiply with the x1, second normal equation, multiply with the x2, third normal equation. So up to k part, you can get this normal equation. So although the process is, we are getting these normal equations from differentiating that summation you had square with respect to beta 0, beta 1, beta 2. From there, you will get these normal equations. But directly, if I can say this simple method, just multiply with the individual independent variables. First, this is for the intercept part, then for the x1, just multiply with the x1, then with the x2, and then for x3, x4, and up to xk. This is the simplest way you can get these normal equations. If you have up to xk, then just multiply till the xk part, and you will easily get this normal equations. In deviation form, the process will remain same. Just with the deviation xk, you have to multiply. Okay, so I was trying to explain you this variance part. This yes, how these formulas are derived. Okay, so let me give you this example. This is I'm taking from Fortianis because in the Gujarati as well they're given, but the derivation part is not given for this two variable model. So it's actually quite easy, and it's not something very difficult that you have to worry about these variances. Okay, I'm taking it from the Fortianis. Just to explain you that how you have to calculate these standard errors. Why this standard error is so important? Because for hypothesis testing we need it, right? In the T formula, if you remember, in the denominator, this is division with the standard errors. Means it is in proportion to standard error. So that's why it's quite important that we need these standard errors. So okay, let me give you this variance example. Let's suppose in deviation form we have these two equations, summation x1 by beta 1 hat. So I'm taking a deviation form. I already explained this deviation form yesterday while we deriving the R square method. Still have any confusion, just go to yesterday lecture, you will get this deviation form. So we have these two normal equations in a deviation form, right? So we need a variance. So from a matrix, this variance is from this, if you write it in a matrix form, its determinant is summation x1 square, summation x1 x2, summation x1 x2, and summation x2 square, right? This determinant of this particular matrix. So the variance formula is like, let's suppose you want variance of first partial slope coefficient, sigma u square. Now I told you from where you will get this value. This value you will get from summation u hat square and minus 3. Now here we are using this sigma square, that is for a population. But in the derivations, I proved you that expected value of sigma u hat square is equal to sigma square. So we can use it in place of it because on an average, these are equivalent to this particular value. With, now we need a variance for this particular matrix. For that, you have to just write this determinant in numerator and denominator. Summation x1 square, summation x1 x2, summation x1 x2, summation x2 square, and summation x1 square again, x1 x2, summation x1 x2, and summation x2 square. Now this is a part of beta 1. So you have to just cancel this part. And the remaining part is the formula of variance of beta 1. Sigma square summation multiply by summation x2 square divide by this cross multiplication. Summation x1 square summation x2 square minus summation x1 x2 whole square. Now just see, is it the formula right? This is for the beta 1. For beta 2, if it's a term of beta 2, then you have to cancel these two parts and you have to keep it this part. Then variance for beta 2 hat is equal to sigma u square multiplied by summation x1 square, and same in the denominator part, summation x1 square summation x2 square and minus summation x1 x2 whole square. So this is for the beta 2 and beta 3 beta 4 so on. So you can get these variances for these coefficients. So I hope you find it quite easy comparatively. Now you have this formula, right? So by solving this particular method and taking under root of that, you will get these standard errors. Okay. Or if you find it complicated, then go by the matrix method. Matrix method, I told you the variance is this method. Just use this sigma square and keep in mind what this sigma square means in matrix. It is u, this is summation u transpose u case, right? And that you have to keep, this is a matrix form. Multiply with this matrix, you will get variance of all these beta matrix from intercept for slope coefficients. So you can go with the matrix method. You can try both this particular method or this method. Choice is yours. So then you will get these standard errors. So this is done. The third calculation is T part. Okay, Siva sir is asking, okay sir, I'm waiting. For T, you have to just put a calculated slope coefficients like beta 2 hat, beta 3 hat, beta 1, or it's a beta 0, beta 1, beta 2 minus your null hypothesis divide by standard error of these. So standard error you already calculated from the variance. Then you will get these three values, all the T values, T statistic values. So I think now you can calculate this together. So can you remove the GS icon on the screen? Okay. Then you will get all these three values, T statistic values. This is why we need these T statistics for the hypothesis testing. And what will be the null hypothesis? We already did it in part 1 and part 2. So I'm not going to again in detail of hypothesis testing, this confidence interval approach, p-value approach, test of statistic approach. So this is null hypothesis for individual significances. Since we don't know any population parameter value, so it is equal to 0, which means it is not statistically significant. And if we reject null hypothesis, it means it is statistically significant. So you have to put here 0 value for all the population parameters, calculated value from your regression results for beta 0, beta 1, beta 2, and standard error we already calculated from the variance, right? So now you have done with these three values: coefficient, standard error, and T statistics. Then next part what we did is R square. Now if it's a multiple regression, then generally we denote it with the capital R square. That's only to differentiate that it is a multivariate regression analysis. If you are doing bivariate, then we write it with the small R square. If it's a multiple regression, we denote it with the capital R square. So what will be the R square value now? Okay, this is the R square value. Yesterday we derived this particular, right, for the bivariate regression. So if it's a multivariate case, then this will be the formula. So let me do this derivation once again so that you can understand this coefficient of determination once again. Okay, so this is we did yesterday, right? This derivation of R square, and uh, I told you these are two formula which are equivalent, that this explained variation by total variation. This is the R square, and this is the derivation. By derivation, we got these results when we put this beta 1 value, right? So this is the derivation we got for R square by bivariate. Now today we have a multivariate case. So let me solve this with the multivariate as well. Okay, so first today we are going to write it with a capital R square. Now this today we have two variables, x1 and x2. Yesterday we only have one independent variable. So this is generally in a deviation form. If I write it, ratio of explained variation by unexplained variation. Sorry, total variation. If it in a actual way you want to write, this is the explained variation, right? And this is unexplained variation. Sorry, total variation. In a graphical form, as I explained you yesterday. Yeah, this part was the unexplained, explained, and total variation. So R square is a proportion of explained variation to total variation. So using this method, let me derive it again with multivariate case now. And another way of writing it is 1 minus unexplained variation upon total variation. Means you can use any of these methods. This is actually from this equation, total sum of square equal to explained sum of square plus residual sum of square. So if you divide this equation with total sum of square, this is actually R square, or if it's a multivariate R square. So either you can use this method or another method. 1 minus R square equal to 1 minus the second part, RSS upon TSS. So this is the another way of using this R square. You can use any of these methods. So let's get to this formula. So we know in the deviation form, the residual part is deviation form of actual y minus estimated y. What is our estimated y? In a deviation form, x1 plus beta 2 at x2. Yesterday we only have beta 1 x1 because we only have one variable. But today we have a two variables, so this deviation form will increase. Now summation, if we take this 1 minus residual form, this is, I can write it as y minus y hat, right? this equation I'm putting here. So ei into ei, it's a ei square, right? Just put these values here. Y minus the value of y hat. Beta 1 hat x1 minus beta 2 hat x2. Now these days softwares will do these calculations just in a second. So you might think how easy is the regression part. But now see, if you have to do it manually, first you have to understand the formulas and then only you can do these calculations. Summation e yi minus beta 1 hat summation ei x1 minus beta 2 hat summation e into x2. This is value for this particular part, okay? And we know that summation u x1 is 0 and summation e1 x2 is also 0. This is either of the property you can use the covariance of residual term with any of the independent variable is 0. In the numerical properties also we did it. And if you take summation, this is these both the parts are not correlated with each other. So from the covariance property, the covariance of residual with any independent variable is 0. So using these two properties, now this particular term will remain only with the summation ei square is equal to summation ei yi, because this both the terms will get equal to 0. So just now again put its value y minus y hat into y1 just multiply this or put this value of y hat beta 1 hat x1 minus beta 2 hat x2 summation yi square minus beta 1 hat summation y1 x1 minus beta 2 hat summation yi x2. Now from the residual part, if I go with this r square, by this particular method, 1 minus summation, this residual sum of square upon total sum of square, cross multiplication, it is summation y square minus summation e square divide summation y square. If we can put these values here, this value we are going to put here. Summation yi square, this particular term, minus all this term. Summation y square minus beta 1 hat summation y1 x2 minus beta 2 hat y2 x2. Sorry, y1 yi. Now these two terms will cancel out, and denominator we have summation yi square. So what will be the remaining part? Beta 1 hat summation yi x1 plus beta 2 hat summation yi x2 divide by summation y square. So this is formula for r square coefficient of determination. So this is the formula if we have a two independent variables. So if you have a k independent variables, just add these terms. Beta 1 had x summation y x x1, then beta 2 had summation y phi I x2 hat x2 plus beta 3 hat summation y3, sorry, yi x3 plus till k. So if you can add this is a, uh, I can say explain sum of square, divide by total sum of square. So using this method, you can get this r square value. So if you put all these values, then you can get this fourth part here, this r square value, 0. What it means is that 22% of the variation in wages is explained by education and experience. Like for this education coefficient, the interpretation is that with 1 year increase in the education, wages will increase by, if it's in a dollar, then $0.64. For experience, with 1 year increase in the experience, wages will increase by $0.07 on an average, because this regression line is on an average. In this way, you have to interpret these results with that. Okay. Then individual significance, how you check individual significance? Let me go with this p-value approach. Let's suppose our level of significance is 5%. So p-value is less than the level of significance. So we can say reject the null hypothesis, and it means that education, coefficient of education, that is 0.64. This particular coefficient is statistically significant. It means education significantly impact wages, or education significantly explain changes in the wages. Similarly, for the experience, again, the p-value is less than 0.5, so we have to reject the null hypothesis. Null hypothesis here is this beta 1 coefficient is equal to 0, or if beta 2 is equal to 0, because we are saying they are statistically insignificant. Or the other way, as I told you, we don't have any population parameters, so there is no other choice that we have to keep these hypotheses, these null values equal to 0. So coefficient is done, standard error is done, individual significance is done. I'm not doing it in detail because of we already done it in a part 1 and part 2. R square is done, coefficient of determination. Yesterday these values were only 16.16 because only we have education variable. Today we added another variable that might be explaining changes in the wages. So R square is getting increased. Now it is a 0.22. 22% changes in the wages now explained by these two variables. This is a goodness of fit. This value lies between 0 and 1. These details tomorrow I'll again take this R square, few properties of this capital R square. That's quite important. And then I think now you don't have any doubt in this. I'm saying that you have to do it manually. I have given you these formulas, right? The derivation for all these formulas, and how these formulas are derived. So you have to put these values and you have to match with your Stata results. Are they matching these values or not? These three values, coefficient, standard error, t, that you have to calculate. Then R square again you have to calculate. Now you have the formulas and you have to send these files in a Skype. I have to check that whether you are doing or not, because you might be think that what is the incentive here? This is the economic principle from the ManQ. People work through incentive. I know people only work through incentive. So let me give you another incentive here. As I told you, although I want to discuss it with all of you here, I think you 2 or 3 are only present here. Now I traveled with 2 or 3 universities, and at many other places I have through email contacts and through chats I discussed this for accreditation part, and so far I'm not succeeded because their charges are quite high. So the last stand is that from my side. Now I'm going to start it by own, means I'm going to start this in a formal way. I am now contacting many other persons, means I'm going to start this center for this research training course. And after this center means for accreditation, the process is now I'm going to accreditation for my own any other university with the private university because their objectives are totally different. Just earning a money, that's not my interest. So I'm going to start by own. For that, the first requirement is government needs some place. Means the registration is not individual from the individual names. They need institutes, right? So I can't build a big institute. That's not possible. But from the beginning, just one classroom center type where I can provide these sources. I'm going to build that, and I'll register that particular center for the government or any other institute, and in future that will be able to provide certificates. Means I'm going to take a registration now, but this process is quite long because first I have to buy a land, then build a construction, that particular classroom type thing. Then I can apply for the registration through contacts from ITs, and many other institutes, or maybe directly from the state government. That I have to see that which option is more suitable. But now I'm going to start that because I can see the potential in these sources, because now you can see that on an average no one is teaching these things in detail, or if it might be they're teaching on the commercial purpose but their charges are 70,000, 80,000. That's not possible. And the sources which I am sharing with you, all these data sets, textbooks, derivations, examples, Stata commands, that's not even nearby the charges I'm charging. So I don't think anyone have any object in the future to join these courses. And most important part, after this series, I want to add other instruments in this series like production functions, translog, uh, SFA, CES, Cobb-Douglas, then PCA methodology, then inequality measures, then input-output models, or many other tools which we study in economics. Might be others need those tools, but for that I need an investment. The only problem now I have that I don't have a big investment, and the cost of land these days in the cities, it's not possible. So the change is that I am now going to shift to the Himachal. There the quite land is quite reasonable, and I already contacted few persons. They're going to ready to help me in this process, and most probably we are going to find a one central location with all the facilities in Himachal. One of those site is in the Himachal is that international paragliding site in our district Mandi that we are now looking upon, and few land opportunities there that we can buy some land there and we can build this center. Although this is something big as a aim for me, but I'm now going to put all the efforts in coming months and years to build this particular thing and get accreditation for that from the government, so that I can continue with this course and add other resources. As I told you in the beginning, my target is to complete 250 hours. This series I'll end with 80 hours or 100 hours. Even this is a quite heavy. If you can look now, all the lectures we started from the beginning and the end, when we complete this advanced econometrics, this is not easily going to available anywhere. So now the target is to complete up to 250 hours. For that, I need investments. So now I'm looking for that, going to discuss with others, going to start one more series from January, and that is quite advanced training course type of thing. From whatever amount I'll receive, I'll put that as investment for the center. And one important thing I'll share with you, that you might think that individually, generally what will happen when I contact any individual or researcher, they think, okay, the calculation is like that. Okay, in my PhD, I need it. Okay, in my teaching, I need it. Okay, let's join. You never realize the importance from the other's point of view. Uh, these days, I'm receiving queries from African countries, from the Pakistan researchers, those who are following these lectures from the YouTube, and they are saying that we really appreciate this effort. Means earlier, I don't have this thought that means someone from the Africa can contact me that this is really good, and they also need these things. So we are helping all others with putting effort. We are helping many others. See, something that is we are not taking seeing in form of practicability, but now you can realize that how much the potential for this type of courses and series if we do it seriously. The thing is that how much effort I'll put in it. As I told you, this need to be balanced between software skills, practical applied part, which we need a data sets, and then same time we need a theoretical background. This type of course is quite difficult to find. Only maybe in IITs few professors are teaching, maybe in JNU, but it's in India we have more than 900 universities, and I'm sure not even more than 15 universities are doing these courses seriously. So that's the potential, and all the researchers need it, not only from the economics, but other backgrounds as well. So keeping all these things now, I'll put my efforts in coming years to build this as a center, not just this online classroom, so that you can join actual classes with me. It might be, and just think that if these classes are somewhere tourist place in Himachal somewhere, everywhere many researchers or many individuals spend so many holidays in hilly states and other places. So why not we can spend time in these type of activities? Same time you can enjoy the holidays and you can learn. Means that's the one thing I have in a mind. And for that I need a coordination from many others, for the land, for construction, for the investments. There are n number of things. Means effort you can't even realize that every day I have to put it in a YouTube, then queries for the Gmail, Facebook, then LinkedIn, then the WhatsApp, then Telegram, then I have to make content, then put the content, share with others, take the queries. I mean, this effort you can't even just calculate that how much effort is this. It take uh, morning to evening, and sometimes I work quite the night up to till 1 and 2 a.m. to just give feedback to the queries which I receive. So this is something quite useful as well. I need your support as well in the future upcoming series. At least you can share these videos, at least you can convince others. Now all the details, the registration form you have filled, if you again you cross check that form, now you'll find all the details there, the next coming upcoming content, the feedbacks, the details, the cost scenario. I updated that form, you can now share with others. Means if you want, for the upcoming part, that contribution will help me to build this structure. And I'll promise I'll add more content. The content I'm going to cover in these 4 parts. After that, I'll trying to add other content which is quite useful in economic analysis. So, okay, that thing just came in my mind. I don't know, because maybe in last few days I'm thinking on that and I'm working on that on the practicability viewpoint. Okay, same time, I want to keep it reasonable so that one can learn these skills as the charges which state universities are charging for their courses, and same time they can learn something practical for their lifetime, because your research thing is not for 1 year 2 years. This is in your teaching and for your lifetime experience. So I hope I'll receive your support for that also. Means, although the details I'll share in the end of part 3 or part 4, that I'm now making that total framework of all those things, means the practicability, how that is going to be worked. But now I have a this next thing in my mind that I have to do that. I'm not going to just stop this online series after this part. I'm going to take it to the next level. So this part is done. Now, as yesterday I told you, tomorrow I'll also cover overall significance of the model. That is the F ratio. So now come to this particular part, and here I'll explain you degree of freedom as well as the this what is this degree of freedom. First, just keep in mind this thing. R square is explained variation upon total variation, right? Now come to this F part where we have to see overall significance of the model. That is okay, this small single equation, if you can see that. Let's suppose here we only have two independent variables, x1, x2, and their slope coefficients are beta 2, beta 3, or beta 1, beta 2. Now our null hypothesis is that jointly their contribution is zero. Means these are not explaining any changes in the dependent variable. Or just one small thing before that, because we are discussing this R scale. what it means now, because yesterday I explained this graphically, and I like this graphical methods to explain this, give you more detailed information. We have a y, okay, like in a Venn diagram form, okay. There are changes in the y variable, as I explained you that yesterday. The y mean, and surrounding all these changes are the deviation of y from y mean, right? That's the total variation. If you take its square form, that's the total variation. So let's suppose this is a total variation in a y, okay, in a Venn diagram form. There is a variation in x1, like we have a wages, education, and experience. Okay, that is our x2. Let's suppose there are changes in the education, there are changes in variation in form of statistics. I say the variation in the x2. All the variations are from their respective means. Okay. So what this R square is telling is that there might be some common variation. Like if I put it in form of Venn diagram, this is a y. Okay. This is x1. This is x2. So this common variation is the explained, we say this is the explained variation divided by total variation of y. That is our actually capital R square. Explained variation by total variation. And in this case, we have this 22, right? 22%. That only 22% of the variation in the dependent variable is explained by independent variables. It might be high, that depend upon these relations. Let's suppose it might be quite high. It might be, let's suppose 70%, 0.70. And it means 70% of the variation y. That's the goodness of it, right? The more this value is, the more the better the model is, that changes in wages are explained by these variables. That is our R square. Now, with this methodology, now we have to see overall significance of the model. First, let me give you this. Okay, simple formula behind this, the F ratio method, that I told you that this F ratio is actually the ratio of variances or two chi-squares that indirectly we use to compare, we use to check the overall significance of the model. So in F ratio model, what actually we do to check the overall significance of the model, that indirectly we compare explained sum of square with residual sum of square. That if this gap is quite high, what it means? It means that, let's suppose this explained sum of square is quite high, greater than this residual. It means the overall significance of model. It say if this ratio is significant, it means this gap is significant. It means these variables are significantly explaining the changes in dependent variables. That's the F ratio, and that's the method for overall significance of model. So in the R square formula, now you can see this R square formula. In the numerator, here we have this part, right? Explained variation upon total variation. This explained variation, this explained sum of square is the numerator part of the F ratio. This part. Now compare these results with your table part. One by one. This first part, sum of square, explained sum of square. This is this numerator part, okay? This is a Gujarati, so here they are using x2, x3. If it's a code Chinese, they use x1, x2. Means only two independent variables are here. If it's more than that, it go up to a k part that I told you with this R square method. It can extend up to a k, depend upon how much dependent variables you have. This is our explained sum of square, explained variation, right? This is the numerator part. We have to compare it with the residual sum of. What is the residual sum of square? This is residual sum of square, summation u hat square. So we have to compare this ratio, but before that we have to divide it with respective degree of freedom. For the numerator, degree of freedom is k minus 1. K is the estimates, okay, number of estimate like beta, including intercept. Or you can take number of variables. This both the way here they are going to be 3 minus 1, that is 2. That's the degree of freedom for numerator, and denominator degree of freedom is n minus k. So here it is n minus 3, and here it is 3 minus 1, so 2, and n minus 3, whatever will the sample size. So in our case, you can see now degree of freedom 2, and because our observations are 526, so 526 minus 3, it is 523. If you divide these respective values, this sum of squares, with this degree of freedom, you will get mean sum of squares. This part, mean sum of squares, after dividing with these respective degree of freedoms. And this F ratio is this, like this 75. This ratio is about these two. 806 divided by 10, 10.60. That is F ratio. This here. Numerator degree of freedom is 2, denominator 523. Let's suppose if you want to see the table values, then you can by this particular method. 2 degree of freedom in the numerator, 523 in the denominator. And F ratio is this mean sum of square of numerator divided by denominator, that is 75. This value you have to compare with the F critical value, and you have to find whether this model is significant or not. So here the null hypothesis is that all the coefficients, slope coefficients which we have here, partial beta 1 and beta 2, or beta 2 or beta 3, it's a Gujarati notation, equivalent to 0. And what is alternate? At least one of them is not equal to 0. It is the alternate hypothesis. Now, if we see our results, p-value is less than level of significance. Let's suppose our level of significance 0.05. So it means we have to reject the null, but it means we are rejecting this hypothesis that it is not equal to 0. At least one of them is not equal to 0. Indirectly, it means our overall model is significant. So this is all the values: mean sum of square, explained sum of square, residual sum of square, divided by respective degree of freedoms. That will give you F ratio value. Now you have to calculate these values because I already give you the formula, right? You have these values, right? In the R square as well, you have these values. Just put these values, you will get all these values. And by putting this value, you will get F ratio, and that you have to compare with the, when we do manually, we don't have p values. So you have to compare it with the critical value from the table. Or as I told you that critical values from the Stata, you can also calculate critical values. So our overall model is also significant. So by this way, now adjusted R square I'll discuss in the next class. That's also important. But beside this, R square and root MSE, this root MSE also one of the property. I'll also explain this in the next class. Except for these, I now described you all these derivations for all these parts. And this is what we will calculate while we apply the regression analysis in any of your relations among variables. Technique might change because if OLS is not applicable, might be some there is some another combination like qualitative dependent variable, then the method is different. But this is the way you will get regression results. So in detail, I explained you all these values. Now I hope you got this all the values. And Gagan, degree of freedom, if you ask me theoretically, it means let's suppose you have 7 different type of dress that you want to wear for the 1 week. You have 7 days and 7 dress. So first day you have a choice of 7 dress, right? Second day, 1 is gone. You have a 6, then 5, 4, 3. But on the last day, you don't have any choice, right? So you lost 1 degree of freedom. Although this theoretical detail, if I go, that's quite detailed. You can Google through the for degree of freedom. You'll find many article on it. I'm giving you just layman explanation for the degree of freedom. Like here, when we calculate, like if you want to calculate the variance, that is summation you had square by n minus degree of freedom. So since we in this case we calculated three estimates, so we lost 3 degree of freedom. So this is n minus 3. So this is the degree of freedom concept. I'm giving it in a simple way, but if you need a detail of degree of freedom, then you find many articles in internet. So that is about the regression. Now I'm only left with these two small concepts that I take in next class and few more examples of multivariate regression, practical examples. But before that, you have to calculate this manually. Then only will understand this process. And then I'll take few more examples. One of the log function, then square of units, you change in the units, a few small concepts in the next class. And after that, then I will jump to the assumption problems, multicollinearity, hetero, and auto. So only one class I take just as a remind for all the basic concepts or few extra concepts so that you can get all the details about the regression. So now we are done with the derivations for this part, at least this part of the series. All the derivations I did in detail as possible, means I tried to give you these derivations from my class notes, from Kotsianis, from Gujarati, from Woolridge, uh, one of the matrix derivations from the William Green textbook. And so I'll try to give you as maximum as possible. These derivations are actually not easy to get all the derivations. So thank you so much. And just think about the proposal I told you about this investment in for the next thing. I'm going to start a next series from the January. I need your support. At least you can suggest to your friends. Means if you ask me that, let's suppose you are doing this series. If you ask me that, can you share about it? Definitely, because if I go calculation wise, there is nothing, the charges something is going to lose, because in return they are going to get these all data sets, derivations, all the notes, all the recorded content. Now, no one provide this 100-hour or 80-hour recorded content with the classroom series. Never. I have never seen this. I'm going to share all the recorded content and all other sources which I have. NSSO extraction. No one teach NSSO extraction, means at these charges. Only for NSSO, people are going to charge 12,000, 15,000. So I don't think cost wise there is any restriction for this. You can suggest to your friends. And I already updated a Google form. So if you have a registration form, means if you want to share it with anyone, you can just share the Google form. Let me show you all the details. And I have changed it in the Google form. Once net it's okay, yeah. Just wait for 1 minute. That's because be quite honest with you. I need this investment which I'm sharing, because I don't want to end this thing. If I took this initiative, so why not it took it to some next level, add some more content. Then besides that, I'm going to add case studies now from the next coming years. I want to make case studies from the research papers, like the mistakes in the published papers. Is all this content need a effort, right? And that I am ready to put, but in the return, I need your support. And as I am explaining you are not only going to help me, means we are helping each other. Like I given you this example, students from Africa, Pakistan, Nepal, they are studying this from these YouTube channels, because this year you also know that how much is the loss in the actual classes. So if one is providing all the content from the internet, it's really helpful for them in their bachelor courses and master courses. So they have now this full-fledged material for econometrics. So there is no harm to share this content. So I changed this form. Now this is the advanced research training course, because from the next coming I'm going to add few things, uh, because to make sure quality in the classes. maximum 30 participants. I'm not greedy person or something that as maximum. No, maximum 30. More than that, it's difficult for me, and I know the quality will get compromised. All the details are in this form, the content, the sources which I am going to share with them, feedbacks if you want to share, already I put here. All this labels, part of the extraction, details, charges, date, time period, feedbacks, and the sources which I am going to share with them. So all these are put in the form, so you can share this if you want among your circle. And it's my humble request. Try to convince them that there is no harm in this course. Because if you think it's like why one could convince others. So my question is there any harm in this course if one is doing? If I'll get chance to learn any of this type particular course, I definitely do. Like the other things I'm saying that translog function, input output models, PCA method, inequality measures, sampling designs, questionnaire test, sampling practical applied problems which we face. That part in coming years I'll work to add with that few more courses, and I'm going to take help from other scholars from different universities. And by the time I'm getting positive responses from many sites, for that I'm thankful to all of you, because I know you are sharing these details already with among your circle. So thank you so much. This is the basic part of this for part 3 that is completed. Now the only we left with the problems of the assumptions that we have to deal and the dummy variable case. So thank you so much, and you're always welcome for any type of suggestions for how I can take it to a next level in future. I'm always open for discussion and debate. So thank you so much.